Hello friends, in our last video we had started our discussion on the current in semiconductor. We were introduced with different aspects of carrier transport, the low field transport and high field transport. And we were also introduced with the term mobility. The current that we discussed in our last video was mainly due to the applied electric field, and it is known as the drift current. Today we will be seeing another constituent of the current in semiconductor, which is the diffusion current. So let's see what are the different aspects of diffusion current. As a recap, more into the previous video, we had considered a collision of electron with the particles and the impurities in the semiconductor for explaining our drift current. Certain notations which I would like to bring back to your memory will be tau, the mean time between collision, v, the velocity of electron from one collision to another. And we made use of simple equations that we had studied in physics, like velocity is equal to acceleration into time, and acceleration is equal to force by mass, or in other words, force is equal to mass into acceleration. By making use of these equations, we had found the equation for drift velocity, which is equal to q tau by mn star into F, which is the force due to the electric field. As you all know, mn star is the effective mass of the electron. The current density can be formulated from this knowledge. The current density, which is resulting from this net drift, is just the number of electrons crossing a unit area per unit time, multiplied by the charge on the electron. So if the unit area, number of electrons, if we take it as n into Vx multiplied by the charge of the electron, which is normally taken as minus q, we will get the current density. So J of x, which is the current density, will be equal to minus q into n into v of x, where v of x is the drift velocity. The suffix x shows that the current is in the x direction. We are concentrating on the current in x direction for our explanation. The negative sign that is there in the equation is to denote current direction is opposite to that of the direction of electrons, which is the convention that we follow. Normally we take the current direction as opposite to that of the direction of the electron movement. If we try to substitute the value of drift velocity in place of v of x is equal to minus q tau by mn star f of x, f suffix x. If we substitute that in the equation number 1, we will get J of x is equal to q square n tau by mn star into fx. This is just a substitution in place of v of x, we are substituting the equation that we had discussed or we had formulated in our last session. And by the substitution, we get the equation for j of x, which is a derivative of an Ohm's law, of the Ohm's law, which is the current density is equal to conductivity into electric field. Current density Jx is equal to conductivity, which is denoted by sigma, into electric field, or the force due to the field applied. Here, since it is an electric field, we call it as electric field, f of x. Now, what is sigma, the conductivity? Just by correlating the equation j of x is equal to q square n tau by mn star into fx, we could easily write conductivity is equal to q square n tau by mn star. And if we just go back a little bit to the previous discussion, we know that mobility mu n is for the mobility for electrons, is equal to q tau by mn star. And by substituting this value in place of q tau by mn star in the conductivity equation, we will get conductivity is equal to q into n into mobility. So the relationship between conductivity and mobility, in this case we are discussing about the electrons, that is why it is mu n. So the conductivity due to electrons is equal to q, which is the electron charge, n is the number of electrons, and mu n is the mobility of electrons. As we had discussed in our previous session, the term drift current, I want to re-emphasize it once again. The current due to the application of electric field is called as drift current. Or in other words, if we apply electric field, the charge carriers will move from one place to the another. The electric field applied is also known as the electromotive force. The force which is created by the electric field helps the charge to move from one place to another. And the current due to this movement is known as drift current. When an electric field is applied across a semiconductor material, there will be a flow of charge carriers. The velocity with which these charge carriers are moving is known as the drift velocity. And the drift velocity and resulting current is characterized by the mobility of the particular charge carriers. As I had mentioned in the introduction, the current in the semiconductor is not purely due to the drift current or the current due to the electric field, the movement of charge carriers due to electric field. There is another constituent to the current in semiconductor, which is the diffusion current. What do you mean by diffusion? The same simple explanation that we had studied in our school days is applicable here. Diffusion is a process where something moves from its higher concentration to the region of lower concentration. Since here we are discussing about the diffusion of the charge carriers, this could be termed as net motion of carriers from regions of high carrier concentration to region of low carrier concentration. And this type of motion is called diffusion. and this movement of charge carriers due to diffusion is also contributing to the current flow in the semiconductor. So in diffusion, due to the variation in the gradient, or there is a gradient, which means the variation of concentration of electrons and holes, that makes the carriers to move from high carrier concentration to low carrier concentration. So in nutshell, the two basic processes of current conduction in the semiconductor are diffusion due to a carrier gradient and drift in an electric field. Whenever we think of diffusion, or to explain diffusion, we take the example of a perfume which is sprayed in a room. If you are spraying the perfume in a corner of the room, initially the concentration of the perfume will be in the corner. As the time moves ahead, the entire room is filled with the fragrance, because from the corner the perfume particles are spreading from the higher concentration to the lower concentration, which is the rest of the room. Similarly, if we inject a carrier at a point, say at an instant x of 0, by and by as the time moves forward, it diffuses. And the graph shows the way it can diffuse to the other areas of the semiconductor. So the graph that is shown in the video is the explanation of how diffusion of the carrier happens if there is a higher concentration at a particular area and it is randomly moving towards lower concentration area through thermal motion, random motion and scattering. Now, in order to analyze how or what are the important aspect of diffusion, we will consider a one-dimension gradient. We are just plotting a gradient. The blue curve is the arbitrary electron concentration gradient in one dimension. We know semiconductor is a three-dimensional wafer. There will be a three-dimensional movement of carriers in the wafer. But in order to simplify our analysis, we are just considering one dimension. That is why we are drawing a curve. The blue curve shows the electron concentration gradient in one dimension. And we are dividing the area under the curve into different segments. Each segment will have a distance L bar, which is also known as the mean free path between collision, which means the distance the carrier has to move before it collides with other particles in the semiconductor. So the mean free path is taken as L bar. And the mean time between collision is tau. On the right side of the graph, we are just zooming into the two segments, which is shaded in gray. Segment 1 and segment 2. We are considering these two segments on the both sides of a point x0. So segment 2 will be from x0 till x0 plus L bar. And on the left side of x0 we are having the segment 1, which is x0 minus till x0 minus L bar. or the area of segment 1 is from x0 minus L bar till x0, and the area of segment 2 is from x0 to x0 plus L bar. Now we will see how the movement of carriers due to diffusion is happening. Suppose you are having n number of electrons in segment 1. The chances of movement of these electrons to the right and left will be equal. Take half of the electrons in segment 1 is moving to the right and half is moving to the left. Similarly, from segment 2, there is another set of carriers there. Half is moving to the left and the half is moving to the right. So if we consider a net movement of electrons across x0, it will be from segment 1, a set of carriers moves to the right. From segment 2, a set of carriers moves to the left. It is the difference of these two movements will give the total number of electrons or carriers moving to the right. Mathematically, we could write it as the net number of electrons passing x0 from left to right will be equal to half of n1 L bar A, which is the, as I mentioned, half of the carriers in segment 1 is moving to the right, half is moving to the left. Now we are just thinking about the number of carriers moving to the right. So if we consider the point x0, the number of electrons passing through that point towards right will be equal to 1 by 2 n1 L bar A minus 1 by 2 n2 L bar A. Another equation that we should understand is the electron flux density. The electron flux density is given by phi n is equal to L bar by 2 tau n1 minus n2. So the flux density, electron flux density in the x direction per unit area is given by phi n L bar by 2 tau by n1, 2 tau into n1 minus n2. Keeping that in mind, we will try to simplify n1 minus n2. Suppose L bar is a small differential length. We know that it's a small length L bar. We could write n1 minus n2 as equal to n of x minus n of x plus delta x by delta x into L bar. Delta x is the small variation in the concentration of carrier while we move from x to x plus delta x. Where x is taken at the center of the segment 1, and while moving a delta x times to the right, we will reach the center of the segment 2. So we are just considering or rewriting n1 minus n2 as nx minus nx plus delta x by delta x into L bar. Delta x is same as L bar, which is the small differential length. So we have done multiplication and division with the same quantity, so there won't be any change in the term. We are just trying to make a simplified form of electron flux density. So the electron flux density equation can be rewritten as L bar square by 2 tau, limit of delta x tends to 0, n of x minus n of x plus delta x by delta x. What we have done is, in place of n1 minus n2, we have substituted the term nx minus nx plus delta x by delta x. Into L. N1 minus N2 was written in a different format in this case, that is being substituted in our electron flux density equation in place of N1 minus N2. From this format, keeping in mind our basics that we had studied in the differentiation in mathematics, we could say, or we could easily rewrite it as dn of x by dx, or in the definition of the derivative, limit delta x tends to 0, nx minus nx plus delta x by delta x is equal to minus dnx by dx. This is the definition of the derivation. So we are just substituting the limit term into the differential term. So now the electron flux density phi n is equal to minus L bar square by 2 tau dn of x by dx. The term L bar square by 2 tau is known as electron diffusion coefficient, which is normally denoted by d suffix n. So we have electron flux density for electron flux density phi of n is equal to minus dn of x by dx. Similarly, in case of holes, we could write hole concentration or the flux density of holes phi p is equal to minus dp dn of x by dx. As I had mentioned earlier, we derive in terms of electrons and relate it to that of holes. So phi n is equal to minus dn of x by dx that we have derived. Similarly, for holes, phi p is equal to minus dp dn of x by dx. This diffusion causes diffusion current. The diffusion current crossing a unit area or the current density is the particle flux density multiplied by the charge of the carrier. If we multiply the charge with the flux density, we get the current. So the diffusion current, electron diffusion current, will be equal to minus of q, which is the charge of the electron, dn of x by dx. That minus and minus will become positive, So which will be equal to plus q dn into dn of x by dx. Similarly, for holes, the diffusion current Jp, in bracket we write diff because we want to say that this is the diffusion current, is equal to minus in bracket plus q, because that plus q is the charge of the hole, dp dn of x by dx, which is equal to minus q dp dn of x by dx. The diffusion current for holes and electrons is different in the sign, which says that electrons and holes move together in a carrier gradient, but the resulting currents are in opposite direction. This is due to the convention. The current direction is opposite to that of the movement of electrons. But in case of holes, it is in the same direction of the movement of the holes. That is the difference in symbol. Now, if we summarize, as I had mentioned earlier, the current inside the semiconductor is due to the drift current and the diffusion current of both holes and electrons. If we just consider the case of electrons alone, the current in the x direction, Jn of x, is equal to q mu n of x E of x, which is the drift current. Only difference with what we had studied earlier, in here we have replaced fx with E of x, because we know it is electric field, there is no other field, so we are using E. So that is the drift constituent plus the diffusion current q dn dn of x by dx. Similarly, the current due to holes will also have two constituents, the drift current and the diffusion current. Drift current of holes is given by q mu p p of x E of x minus q dp dp of x by dx. So in nutshell, the total current inside the semiconductor is due to the drift and diffusion current of both electrons and holes. So whenever we discuss about current in a semiconductor, we need to understand what is a drift current and what is a diffusion current. Drift current is due to the applied electric field, and diffusion current is due to the change in concentration of the carriers inside the semiconductor. If we try to differentiate between a diffusion current and drift current, these are the points that should come into your mind. Diffusion current, movement caused by variation in carrier concentration. Drift current, movement caused by electric field. So, and the difference in equation is also discussed in this session. So in a nutshell, the current inside the semiconductor is due to both diffusion and drift of holes and electrons. With this, we will stop the discussion on the diffusion current. In our next session, we will be moving on to few relations, few equations, and we will also discuss about Hall effect, and we will try to understand more about semiconductors. Thank you.